Chapter 3, number 21. Refer to the figure for the following questions. Is the magnitude of vector A plus vector D greater than, less than, or equal to the magnitude of vector A plus vector E? And is the magnitude of vector A plus vector E greater than, or less than, or equal to the magnitude of vector A plus F? So I'm going to make some names so we can talk about it. So I'm going to define that G is A plus D, and H is A plus E, and J is A plus F. Just give us some stuff to talk about. So let's actually sketch these guys out. If we sketch A, and then we add D, we would get G. And if we add A, and we add to that E, then this guy ends up being H. And finally, if we have A, and here's the tricky bit, I have to add what is essentially E but the other way, and this will give me vector J. So by I, certainly a really quick answer is that clearly G is shorter than H, and H and J are the same. So those are going to be our short answers. I'm going to answer B first because it's a lot easier. Since I'm adding the same components but just opposite sign, in other words, that H is A plus something forward but also something to the right, and J is the same thing forward, so they have the same Y component, and has the same amount to the left. When we get our magnitude of, for instance, H, all right, if we find what H is, it's going to be the square root of HY squared plus HX squared, and J is going to be the square root of JX squared, JY squared plus JX squared. And here's the key bit. This and this are the same, and it turns out so is this, because HX and JX are the same except for sign, so that when I square them I get the same thing. So that settles that pretty quickly, that part B ends up being equal to. Proving part A, which is sort of physically obvious to the eye, turns out to be a kind of grungy algebra. And I'm going to run through it, but it's probably more than the thing you should really say, oh, I see how to do that. I think it makes intuitive sense in that we are extending both the x and y components in H, whereas we are shrinking the y component for G, and so we find out clearly H will be longer than A, whereas G would be less than A, and therefore G would be less than H. But to show it, we would go about saying something like, okay, so we would have something along the lines of that G would be the square root of gx squared plus gy squared, and gx is ax plus dx, which has to be squared, and gy is ay plus dy, which has to be squared, and then we square root it. To make life a little easier, I'm actually going to go for g squared, because then I can stop carrying the square root around. It doesn't matter, right? If g is bigger than h, then g squared is bigger than h squared. So we know they're all positives anyway, so we'll be fine just doing that. So we end up with ax plus dx quantity squared plus ay plus dy quantity squared, and then we apply the rule of algebra that x plus y squared is x squared plus twice their product plus y squared, and likewise for the y's. You can already see how this is becoming terrible, although it is really just a matter of persisting. There's nothing in it that's interesting anymore, and we're left with that g squared. Actually, I'm going to go down to the screen so I have some room, but we'll be left with what g squared is equal to. So recapping from the previous screen and just rearranging a little, we get that g squared is ax squared plus ay squared plus dx squared plus dy squared, but also these so-called cross terms or mixing terms, ax, 2ax dx, and 2ay dy. And now I'm going to sort of do a shortcut. I'm going to say, well, if I had done this thing for h instead, I would have ended up with exactly the same form of things. Instead of having ax plus dx, I would have ax plus ex, and I'd have to square it, and I'd have ay plus dy, and I'd have to square it. And so I would end up, without having to do too much thinking about it, I hope, I would end up with a thing that looks very similar. In other words, I still get the ax squared plus ay squared. Now I get ex's and ey's here, and I get ex and ey here. And now our key thing that we're going to notice is we're going to say, oh wait, but in our vector, if we sort of remember it, that we had that d went something like this, and e went something like that, which means they share the same x term, right? So we end up with that dx equals ex, because we can see that that's the leg for both of them, but dy is minus ey, because whatever d goes downward where e goes upward. And then these two things imply to us that, well, when I square dx, I obviously get ex squared because they're the same number. And when I square dy, I get minus ey quantity squared, but minus 1 squares to 1, so I actually still get ey squared. So I can go back up here and I can replace what we have with things in e. And you might say, wow, that's a lot of math games. What does that get us? But notice something kind of interesting about what comes out here, that when I compare g squared to h squared, we have this term is the same, and 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 this term is the same. But this term, at the end, one of them is minus, and the other is plus. So that tells me that g squared is something minus something, whereas h squared is the same original thing plus something. So that tells me that g squared must be less than h squared. Right? Because g squared is a thing minus something, and h squared is that thing plus something, plus the same something. But then g and h are both known to be positive, so that tells me that g must be less than h, which is what we had originally, what we saw by eye. In a testing situation, this is a pretty intense, somewhat geometric type proof and would not be a thing you'd be asked to produce on the fly, but you should be able to sort of recognize and sort of intuitively get to why a plus d would be shorter than a plus e.